Okay, let's take a look at the chain rule. I kind of have two different versions kind of written down. The first one says dy dx equals dy du times du dx. Now remember, this is eventually the goal of almost all our problems involving derivatives. We want to take the derivative of y with respect to x. And this says, how do you find that? Well, you take the derivative of y with respect to u times the derivative of u with respect to x. And again, I'll get into that notation a little bit more. And this is a different version. This is saying, well, y is some composite function f of g of x. Again, this is not product. This is not f times g. This is f of g of x. And how do you take the derivative? Well, y prime is equal to f prime of g of x times g prime of x. Okay, g of x here is the argument in f prime. Again, this is not f prime times g of x. This is f prime of g of x. Let's do some examples, and then I'll kind of break it down on how this actually works. We'll start out with some easy examples. Okay, so let's say the example is y equals e to the 4x. And again, don't overcomplicate this. This is kind of an exponential function, e to the x, but then this itself is its own linear function, 4x. And so how do we do this? Well, lots of people will start talking about the outside versus the inside, things of that nature, but I would say that the big rule here is that this is an exponential, and we know that the derivative of an exponential is e to the u times u prime if you looked it up. Again, the derivative of an exponential is the exponential itself times the derivative of the inside, or in this case, the top function, times 4. This e to the 4x is this part. It's the derivative of our big function without changing the argument times the derivative of the argument. Or the exponential e to the 4x is the dy du times du dx, which is this. All right, take another example. How about sine of x squared? Again, the derivative, y prime, is going to equal cosine of x squared times 2x. Again, dy du, the derivative of the big function, sine is cosine, times du dx. This is my u. It's the inside function. It's the second composite function. It's the g prime in this notation. So this is f prime of g of x. See how the argument didn't change? Times the derivative of the inside, which is g prime. Again, it's still e to the 4x times 4. It's still x squared in the trig function, but I took the derivative of sine and got cosine times 2x. Okay, what about if it was a logarithm? Y equals the natural log of, we'll say, sine x. Well, we got to take the derivative of a logarithm. The derivative of a logarithm, again, that's the big rule here. That's the dy du, that's the f. It's the outside function. The outside function is a log. The inside function is a sine. So taking the big rule, the derivative of a logarithm is 1 over the logarithm, and then we have to multiply by u prime. So in this case, cosine x. If you wanted to simplify that, that would just be cotangent of x, but that's not really necessary. That's certainly not what we're looking at to do here. Again, we're all looking about the chain rule. It doesn't matter if it's an exponential, a trig function, a logarithm. It can just be a nice, easy power rule situation. We could have y equals 2 3x plus 1 to the 4th. So the big rule here is power rule. Bring the power down. Argument stays the same. Decrease the power by 1. That's this piece. And then times the derivative of the inside. The derivative of the inside is 3. All of these hopefully share nice easy things in that we're looking at a big rule and then an inside rule, an outside and then an inside, a big rule and then a small rule. Okay, and again, formally this is how you do it, but the chain rule, it still goes back to, do you know the derivative of an exponential? E to the u prime. Do you know the derivative of a sine function? Again, the derivative of sine is cosine u times u prime. Cosine of u times u prime. The derivative of a logarithm is u prime over u, or 1 over u times u prime, same thing. Over here, this is bring the power down, decrease the power by 1, times the derivative inside. All your x rules are now u rules, and they all have this u prime at the end of it, which means we're always multiplying by this. There's your u prime. There's your u prime. Okay? I'm going to show you formally how this works, or maybe even why this works. Okay, so what I'm going to do is I'm going to make up some kind of crazy letters that you might not see much of. Let's say we have some function m that's equal to r to the fourth. What if I said find the derivative of m with respect to r? Well, that's easy. Again, we're not taking the derivative with respect to x. We're taking the derivative of m with respect to r. So that would just be 4r cubed. What if I had a function over here, though, that I said, well, you know what? R is equal to sine of some w. Okay, well, what's dr dw? Well, dr dw is just the derivative of sine, which is just cosine of w. But if I put these things together, what if I wanted the derivative of m with respect to w? Well, dm dw is in fact dm dr times dr dw. If I just fill in here, this would be 4r cubed times cosine of w, but I know what r is. R is sine of w. And I would get that. Okay? This is kind of me writing it all out. And what if we never even knew about this whole r thing? What if we just said then m is just sine of w to the fourth? What if we made the substitution and then go back to what we previously learned? How do you take the derivative of a composite function? This is a power rule in a trig function. So if we want dm dw, take the big rule first, power rule, bring the power down, decrease the power by 1, and now take the derivative of the inside, that u prime, and get cosine of w. And again, whether you eventually would design it like this is just straight up being kind of overboard with composite functions. M is some function of r is some function of w. Well, we want to take the derivative of m with respect to w. We wouldn't necessarily separate this. We would just do it like this in terms of making a substitution. But the chain rule is all about how do you take the derivative of something more complicated than just sine x, e to the x, cosine x. This tells us how to take the derivative of e to the 4x, sine of x squared, logarithm of sine x, cosine of 3x, things of that nature. And again, most of the time in the real world, we're going to have more complicated functions than just kind of the basics. Okay, hopefully this video kind of got you started on the chain rule, but you can take a look at it. But again, if you are struggling with the chain rule, make sure that you know your basic rules of how to take exponentials, trig functions, logarithms, power rule. And again, when you think of the chain rule, certainly it still applies to even the product rule. So you could have a product rule, let's say y is equal to e to the 2x times sine of 3x. Again, the big rule here is a product rule, but you still have to apply the chain rule. Again, the product rule is going to say that y prime is u v prime plus v u prime. U is just your first function, but when you take the derivative of v, v is its own composite function. It's sine of 3x. It's just not sine x. So you got to be careful that the derivative of that is cosine 3x times 3 plus the second function, and then the derivative of an exponential is e to the u prime, e to the 2x times 2. So it doesn't matter if you're doing product rule or quotient rule or any other rules you're going to learn, you always have to apply the chain rule. The chain rule is how we take derivatives of composite functions.